Hello, my name is Stefan, and I want to show how the LLVM ORC JIT can benefit from ThinLTO summaries. If you are not familiar with ThinLTO, just a second, you may want to have a look at the documentation that I linked here. The only thing we need to know in the next 5 minutes is that it allows us to reconstruct the call graph without parsing bitcode files, and this is very interesting for JIT. When I say JIT, I mean IR to machine code compilation, and performance or overhead always means compared to precompiled execution. In general, we can compare or distinguish between two types of JIT. The eager JIT compiles everything up front, so we see a high overhead at load time and regular native performance during runtime. The lazy JIT, each function would be compiled before its first call, so we save a lot of work at load time, but the necessary compiler interceptions cause a slowdown at runtime. A JIT that exploits extra information from module summaries promises to avoid these slowdowns and even load faster. Let's have a look at the load times first. In order to know which functions exist, where they are defined, and what linkage type they have, a lazy JIT parses bitcode, at least partially. On the example of the Clang CodeGen library, this takes around half a second, as we see here on the left. A ThinLTO JIT gets all these information from reading module summaries. This is not only faster, as we see on the right, but it also means that we can do bitcode parsing as an on-demand action at runtime. If we move even more work to the runtime now, how would we avoid a slowdown there? Well, I want to demonstrate that on the example of TinyExpr, which is a library to evaluate arithmetic expressions. In this example, I want to use a color coding. All of these functions can go from undiscovered gray to discovered green, compiled yellow, executing red. To evaluate an arithmetic expression, our JIT will be asked for the address of our entry point, TE_interp, on the very left. A lazy JIT would compile this one function in return. The ThinLTO JIT searches for the entry of this function in our combined index and uses it as a first discovery route. From there, we traverse outgoing edges to discover potential future callies. In our simple example, let's say we always discover 2 hops from our root node. And whatever we find, we aggregate into one compile job. Now we finally parse all those bitcode files that define our just collected functions. And we compile them all in one go. We will always have a small overhead like this for our entry points, but here we saved even a few future interceptions already. In order to anticipate later interceptions, we have to track the path that execution takes through our call graph. For that, we insert lightweight notification stubs between our functions. When the host now calls into our code, execution passes through those functions, and this tells the JIT to spawn new discoveries in the background. In this example, we are discovering from TE compile and find the new function expr, which turned green now. In the meantime, execution continues running as if nothing happened. The new ORC JIT supports multithreading. This means we can also compile our newly discovered functions in the background. This is indicated with the small progress bar here. So while execution continues running, we spawn a few more discoveries and start compiling more functions in the background, and we hope to be fast enough to have them ready before execution reaches them. In this case, we have no interruptions during execution and get very close to regular performance, like the eager JIT. This is the idea. So far, I only proved the basic assumptions, and in practice, of course, this needs a little more intelligent tuning. But once this works, I thought, why not build Clang stage 1 in memory? There's some good evidence that this could speed up our distribution builds. Clang executes only half of its own code to compile stage 2, and on top, we may benefit from pipelining because stage 2 builds can start earlier if they don't need to wait for stage 1 to be linked. This is only speculation for now, but maybe we can figure it out. Thank you.